Do you know where did we stop? Yes, is this? Please tell me, where did we stop last week?
The next 3 slides.
Okay. Not those time. Yes, okay, because last week.
32. 32.
Is this one? Is this one because you are talking? I'm not hearing something from you, so that's why I would like to ask you again. This line or not? Or maybe is this line?
Yes.
Yes. Okay. Yes. Okay. Okay. I think it's better for me to talk a little bit about the two previous line. So why is that? Because in this class we get a lady come from the Sri Lanka. So that's the reason why if I talk something in Vietnamese and sometimes she didn't understand. So that's the reason why I'm trying to teach. I'm trying to teach in English without in Vietnamese. And also in the side, I think you are trying to understand something in English without Vietnamese. I think it's better for both of us. Yes. Okay. And okay. So let me introduce a little bit about the previous slide. Last week we stopped talking about this because we were talking in Vietnamese, and now I am talking in the English. And for this slide, you can see. And last week I ask you to answer. For example, some people are sitting here. For example, actually are sitting in this pro line. Okay, they won't be nice because they want to be electrocuted. Why that? Because there are no different voltage between them and and the land. Why that? Because they are sitting in the line with the same level, with the same level of voltage. So that's the reason why we don't get the partial recharge between the human between the power line to the through the human to the land. Okay, and for that, and of course, I advise all of you not to do like this. Even when you come back to the countryside, if you if you see the electrical installation is not it's not so that for you it's not so that for you to touch directly directly the electrical system. Okay, it's very dangerous for all of you. And of course, for the slide I would like to show you, and from this slide, last week we were talking about the voltage transformer, and of course, that the function of the voltage transformer is, and of course, if we are talking about the definition of this one, it's also an electrical device, static electrical device, which transform from very, very high voltage, such as 110 or 220 kilovolt, even to 100, 500 kilovolt to very, very low voltage. And output standard of this one is normally 100 volt, or 100 divided by square root 3 volt. Okay, and what is application of this one? And as I said before, the application of this one is for the protective relays in electrical system, and also in application for the system of the measurement. Okay, system of measurement. Because normally for very, very high voltage, we cannot measure directly by the instrument, some tool. For that, if you want to see the values of the voltage, and also if you want to measure the values of the voltage, of course we have to measure the voltage transformer like this. Okay, so that's the reason why I like to teach you about the concept of voltage transformer. Okay, and of course when you do the middle exam or the final exam, you can see sometimes they will ask you what is the difference between the they will ask you what is the difference between the voltage transformer and the normal transformer. And the normal transformer also. Okay, and keep in mind this concept is very important. And if you understand very well, and for that, it's very easy for you to select the best answer for the questions. Okay, because when we do our exam, even for the middle exam or the final exam, we have to do some tests with the multi choice. Okay, without writing exam. Okay, for the multi choice. Okay, and of course for each lesson. Okay, I would like to emphasize and some theory appearing in the middle exam or the final exam. Okay, and for this slide, we are talking about the current transformer. Okay, and of course, if we are talking about the definition of the current transformer, it's also static device. To transform from very high current value to very low current values. Okay, very low current value. And the output standard of the current transformer is 1 ampere or 5 ampere. Okay, it's 1 ampere or 5 ampere. I'm writing here 1 ampere or the 5 ampere. 5 ampere. Depending on each electrical device. Okay, and of course they will ask me, and what is are you steering? Are you hearing? Are you still hearing something from me or not? Because on my side, I see the bad network quality.
Yes, still.
Okay, thank you. Okay. Because I'm not sure that because the quality of the internet, I'm not sure on that side is still good or not. Because in my side, I see the sound quality is bad. For that, I have to check internet connections and try to talk a bigger. Okay, and you can see the output standard of the current transformer. Have a look at this slide. You can see normally it's 1 ampere or 5 ampere. And of course, and the question is that what is the application of the current transformer in practice in the electrical system? Okay, because this one is also for the protective relays and the system of measurement. So why that? Because you can see when if we have something like, if for example, if you measure very high current value, okay, we cannot use directly. We cannot use the tool directly to measure. Okay, of course we have to measure through the current transformer like this. And for that one, when you see something in the electrical box, or if you go to the transformer station, you can see there are a lot of current transformer and also voltage transformer. Okay, transformer. And for that, the current transformer and voltage transformer play an important role in electrical system. Okay, electrical system. Okay, and of course, now the idea that, and okay, so we understand very well about the application of the current transformer and also the voltage transformer. And of course, if you want to connect the voltage transformer to the electrical system and also for the current transformer, and how to connect. Okay, in order to answer these questions, okay, I would like to show you a next slide. As I said before, okay, because next slide that we stopped talking last week here. Okay, of course, appearance of this slide. If you look at this slide, okay, can you guess what is the application? What is the current transformer and also the voltage transformer? Okay, from the left hand side to right hand side, you can guess. Okay, and of course for my teacher, okay, for me it's very easy for me to answer. Okay, I can't answer right away about this. Okay, and of course from left hand side to right hand side. Okay, please answer. What is the voltage transformer and what is the current transformer? It's very easy. Okay, of course, if you go to the laboratory, okay, to lab and okay to do some experiment, okay, you have to connect some tool. Hello.
The left is a current transformer, right?
Yes, okay, but because the signal is still very good. The signal is still very good. Yes.
Yeah, it is.
Okay. Thanks. Okay. Yes. And here, okay, from left hand side to right hand side, okay. For example, let's say again, when you go to the laboratory, okay, to do some experiment, you have to use some tool, okay, some electrical device, okay, some electrical device. There's some problem with internet. Yes. Now is this okay? And for that you have to connect all electrical device together. Okay. And for that you have to take care of instrument like a current transformer and voltage transformer. Okay, how to connect? Have a look at this one from left hand side to right hand side. Okay, you see right away. It's right away for the current transformer must be connected to the electrical system in series. Because for the ampere match, even for the ampere match, okay, if you want, you have to use the ampere match, okay, to measure, okay, to measure the current value. Okay, for example, if the current value is very low, it's no problem for the ampere match. Okay, so if you see some trouble, for example, if the current value is very high, it's very high in comparison with the scale of ampere match. Okay, and for that you cannot directly ampere match to measure current value. Okay, and how to do? Of course, for this guy you have to use the current transformer. Okay, to measure current values of the system of electrical system. Okay, and in the same way for the voltage. Of course, have a look on the right hand side. On the right hand side here, you can see the voltage transformer is connected to the electrical system in parallel without series, in parallel. Of course, when you do the middle test or the final test, okay, you can see the will show you. Okay, they will give you the picture showing you the electrical device connecting directly to electrical system in series and in parallel. Okay, and they will ask you what is where is the current transformer and also where is the voltage transformer. Okay, and of course for that you have to know the best answer for selecting. Okay, and for this, okay, I would like all of you to understand what I'm saying. Okay, what I'm saying, and for the left hand side and right hand side, and of course here you can see, yes, you can see, and this is for current transformer, and this is for the voltage transformer. Okay, and of course, for example, if they ask you to answer what is the difference between the current transformer and voltage transformer, okay, I think all of you understand very well. Okay, and for this slide, because the last week I stopped talking about this slide, and also I was explaining something in Vietnamese, but for the lady, for the student coming from the Sri Lanka, so she cannot understand. Okay, she cannot understand something speaking in Vietnamese, and for that, and from today, I'm trying to teach you in English without in Vietnamese, and also for the side. Okay, I think you also try to understand in English. Okay, for example, if you don't understand very well something that I'm teaching, okay, because after here you can take a phone call, okay, take phone call direct to me, okay. I will explain to you in Vietnamese, and also you can, another way, you can email directly to me, okay, and for that, okay, we can discuss something in Vietnamese, okay. But hopefully I would like all of you to practice in English. I think it's better for all of you, because for this program, so when you graduate from this university, okay, you can apply scholarship for the master thesis, and after that you can apply scholarship for the doctor thesis also, because I know that one of you, after graduating, you become an engineer. Okay, you can work for the company, and also you can work for the university. If you want to work for the university, of course you have to continue to study master thesis and also the doctor thesis. Okay, because if you know well English, there are so many opportunities for you to apply to get scholarship in Europe country. Okay, in Europe country also. I hope. Okay, and this slide we stop. This slide is okay. Hopefully you understand very well in these three slides that I have just been talking about that, and. For next slide, we are talking about the construction of transformer. Okay, and up to now, all of you know well about the definition of transformer, and also the concept of transformer, and of course for the application of transformer and functions, and for example, what is the transmission transformer, what is the distribution transformer also. Okay, also, and for that, if you understand very well the application and the concept and the concept of transformer and the function of transformer, and from this slide through the end of this chapter, I think it's not so easy for you to not to understand. Okay, it's very easy for you to understand. Okay, and in this slide, you can see, have a look at the picture. Quickly, you can see this is the magnetic circuit of the transformer. Okay, and before talking about that, you should know. So you should know the construction of transformer. It includes two main parts. The first one is iron core. Another code name is magnetic circuit. So iron core is for carrying the magnetic field due to the current flowing in the winding, okay. And the second main part of the construction of transformer is the windings. For the winding, we get two different winding. The first one is the primary winding, and the second winding. It's normally the primary windings either is either high voltage windings or low voltage winding, depending on the step down transformer or step up transformer. For example, if we are talking about the step-up transformer, it means that the primary winding is the high voltage winding, and of course for the secondary winding is a low voltage winding. Okay. On the other hand, if we are talking about the step-up transformer is mean that the primary winding is a low voltage winding. Okay, and of course for the secondary winding is the high voltage winding. What is a different? Okay, and of course when you read some textbook, or even if you go to the internet, you can see directly the concept of what is the primary winding and the secondary winding. Okay, and I said a few seconds. You can see depending on the application of the transformer. For example, if the step-down transformer, let's say again, a step-up transformer, you can distinguish what is the primary winding for the high voltage winding or for the low voltage winding. Okay, the voltage winding, and of course, besides the main part of the construction of transformer, we have also other things such as the cover insulation, the cover, like you can see the tank of the transformer, and also the conservator oil. Okay, porcelain, the porcelain submarines, and so on. Okay, and so on. Transformer. Yes, and now it's time for us to talk about the iron core or the magnetic circuit of the transformer. Have a look at the picture. And the picture on the right hand side, you can see clearly about the iron core of the transformer. Is matched by the thin lamination to create a closed magnetic circuit used for carrying main magnetic circuit and so on. Okay, and of course here you can see there are a lot of thin lamination. Thin lamination are matched together in order to get a magnetic circuit like this. Okay, so the question is that, so why do you have to use a lot of thin lamination instead of using the block? Because if you use a lot of thin lamination, okay, of course we have to produce difficultly for that. And the question is that, so why for the magnetic circuit of the transformer, why do you have to use a thin lamination instead of using a block one? Okay, block one. And of course the question is that we have to use the thin lamination in order to reduce the distribution of eddy current, and also we can say yes, of eddy current, and also to reduce the hysteresis losses, because when we get the distribution of magnetic flux through the iron core, and the distribution of eddy current will appear on that. And for that, if we don't use a thin lamination, of course the eddy current losses are very high, and for that temperature appearing in the magnetic circuit are very high, and for that is very dangerous for the primary winding and the secondary winding. And of course the total losses are very high, and leading to the efficiency of the transformer is very low. So that reason why for the engineers and even for the manufacturer, for the factory, for the technology, okay, they are trying to think many ways to reduce the distribution of eddy current, and also eddy current losses, and also hysteresis losses. And for that, not only the magnetic circuit of the transformer, but also for magnetic circuit of other electrical device. Okay, they have to use a lot of thin lamination to reduce eddy current losses, and also for each thin lamination here, you can see it's cover electrical varnish. It's cover electrical varnish to reduce hysteresis. Okay, is covered by the electrical varnish to reduce hysteresis losses. Okay, sure, right. And of course, if you look at around surrounding of this one, you can see some tool to fix the thin lamination together. And of course, this one you can see here for the core, and this one you can see if you look at from the top to bottom, you can see, and this one is core. For example, we get the winding of phase A, okay, wrapping around this one, and of course, and if you next core is the late cause for example for PB for the winding of PB, and of course here for PC. Okay, for phase C also, and of course, and for this one you can see we get the three-phase transformer with a three single core here. Okay, of course, what is this? If you look at this one, you can see this one is the top yoke, and of course it's bottom yoke here, and of course, and some people ask me what is the material for making thin lamination here. Of course, material here is you can see like some carbon and other material to produce the thin lamination. Yes, thin lamination. Yes, of course, this one. And of course, you can see if you look at this carefully, you can see some line like this one, because it's the truck between this one, and of course, even you can see here is very, very small. But if you make a zoom, you can see here the aircraft between this lamination and that lamination. So that's why in the magnetic circuit exited the diffusion of the no load current in the magnetic circuit here. Okay, no load current in magnetic circuit here. Okay, and of course, and for next slide, I would like to show you clearly. Okay, about the position of the winding primary winding and the secondary winding. Okay, and for that, have a look at this. One. Yes, you are still hearing something from me. Yes, have a look at this one. In this slide, of course, you can see, of course, for this slide, it's converted from the previous slide, converted from this one. Okay, of course, for this slide, show you the picture with two different windings, Okay, you can see, but in Vietnamese we denote this one and that one, and that one is the T or the core. Is the core for the including the windings of the transformer. Okay, for example, and 1, 2, 3. 1, 2, 3 is corresponding to three phases of the transformer. For example, next slide again, and phase A, phase B, and phase C. Phase C, okay, and for each phase. If you look at this one, okay, for each phase, how many windings for each phase? Okay, can you answer me the questions? Okay, how many windings for each phase? How many windings for each phase? Who do you know my questions? Who do you know my questions? Can you answer my questions? If you look at this slide,
there are 2 windings for each phase.
How many? Can you repeat, please?
True writing.
Okay. Yes, because you look at this, you can see for each phase, okay, containing two different writing. Okay, the first writing, you can see if you look at carefully, you can see two different color each writing. For example, here written the blue color. Blue color stand for the secondary writing, and two colors stand for the primary writing. Of course, the number 3 is magnetic circuit. Magnetic circuit or some magnetic circuit or some textbook written iron core. It's the same meaning, but with different coding. Okay, and here, of course, as I said before, sometimes secondary wiring. The secondary wiring is for the low voltage wiring, and also for high voltage wiring, and of course for the primary wiring. Primary wiring is for the low voltage wiring or high voltage wiring, depending on the transformer. Depending on the transformer connecting to the electrical system, the step down transformer or the step up transformer. Step down transformer, step up transformer. Okay, you need to understand very well about this concept. Okay, and for that you never, okay, because if you don't understand, sometimes you will make a mistake. And okay, and here you can see, and of course the question is that if you look at here, for example, everything is like this. Okay, and the blue color for the secondary wiring is next to, okay, put next to the, because the is located next to the iron core, next to the magnetic circuit, and the primary wirings is located far from the magnetic circuit. Why that? Okay, why that? Okay, for example, here at the transformer is the for example is the step down transformer. For example, step down transformer here. Okay, if you are considering for the step down transformer, okay, I would like to ask you why does the secondary windings located next to the magnetic circuit, and of course far from the magnetic circuit for the primary winding? Okay, why that? Okay, can you think about these questions? It's very interesting questions. I think so. Yes? Who know my questions? Who know my questions? No? Okay, so I think I would like to call all of you.
Em thấy em Triển nói được không ạ?
Yes, go ahead.
Em
Don't hesitate.
Từ trường tạo ra bởi cái trường điện từ tạo ra bởi cái loại sắt thì nó sẽ không ảnh hưởng lên cái quận sơ cấp nữa, quận primary winding nữa, thì nó chỉ ảnh hưởng đến quận secondary, tạo nên dòng điện là secondary.
No, I think it's not like that. But I think you can even you cannot speak. You cannot explain to me in English. But I think you should try to explain in English, because in our class we get a student. Okay, we get a student coming from the Sri Lanka. So, and for that, for each question, you should try to explain in English. It's better for all of us. Okay, And so the question is not correct. Okay, it's not correct. And
teacher,
yes.
I think the primary winding is closer to the core because it produces the smaller electric flux.
Anything else?
And thus produce the smaller electric. That's what I think.
Yes, but it's still wrong. So why that? Okay, let me explain to all of you. Let me explain to all of you. And normally you can see when we are talking about the location of primary winding or the secondary winding. Okay, you need to take care of insulation, electrical insulation of the winding, okay, of the winding. Because if you are talking about the diffusion of magnetic flux, even for the main flux or the freezing flux or the leakage flux here, okay, here, because even we are talking about that, because and for the magnetic circuit, all the you can see because of due to the magnetic circuit, and for that all the magnetic flux go through the magnetic circuit here, through the magnetic circuit here. But for this, for the location of the windings, location of the winding, of course, we are talking about the reasons why do we have to put, we have to locate or to put the secondary winding close to the iron core, and the primary winding is far from the iron core because of electrical insulation. So why that? Because you can see, for example, if we are designing the high voltage winding of the transformer for example, to 22 kilovolt, 22. When we are talking about the high voltage, we are thinking, so we have to think about the electrical insulation of that voltage level, Okay, for example, here, as I said a few minutes ago, we are considering for the step-down transformer. Step-down transformer is mean that we have to convert, or we have to transform from very high voltage of 22 kilovolt or 35 kilovolt or 110 kilovolt to very low voltage, or to the low voltage level. For example, the voltage level that we are using 220 volt. Okay, for doing that we have to use a step-down transformer. Okay, step-down transformer. So you can imagine that for the step-down transformer, for each phase, secretly from the left-hand side to right-hand side, we get two different winding. Okay, one winding for the high voltage and one winding for the low voltage. And of course, for this case, and for blue color is for low voltage, and the red color for the high voltage winding. It means that for the high voltage winding, is located far from the iron core in order to answer electrical insulation between the high voltage winding and the magnetic circuit. Okay, so why is that? Because if you read the Vietnam standard talking about the electrical system of the voltage level, for example, for the voltage level of 22 kilovolt, you have to check, and they have 22 kilovolt calculated by, for example, from the high voltage winding to the magnetic circuit is the 10 centimeter, for example, 10 centimeter. because from here to here must be 10 centimeters. Okay, for the 22 kilovolt. Of course 22 kilovolt. Okay, and for that, when you use a high voltage wiring, okay, you have to be answer. Okay, you have to be answer that. And the distance from the high voltage wiring to the iron core. Okay, and of course you can see the distance between here. You can see is the air. Is the air. Okay, and in order to take advantage and between the high voltage wiring and the iron core, okay, they have to put the low voltage wiring in the middle between the high voltage wiring and the iron core. Of course, and the question is that, for example, if we don't want to put the secondary wiring in the middle between the high voltage wiring and iron core, is this okay or not? According to you, is it okay or not? According to you, for example, and here, okay, in order to answer the distance between the high voltage wiring and the magnetic circuit, okay, and now we have to put the low voltage wiring in the middle between the high voltage and the iron core. Is this okay or not? And of course, it's okay. Okay, and for that we save the length of the low voltage wiring. Okay, and now, for example, if the student asks me to move the second primary windings, to move the second winding in the middle. Okay, in the middle between the high voltage winding and the iron core to outside of this one. Is this okay or not? Of course, we can do that. But if we do that, but we have to keep the same distance between the high voltage wiring and the magnetic circuit like this. Okay, we cannot move the high voltage wiring next to close to the magnetic circuit. So why is that? Because normally when you check the BNF standard, you can see the distance, the safety distance between the 22 kilovolt to the magnetic circuit must be 10 centimeters. And for that, even when you move the low voltage wiring to outside of the primary wiring, is okay. But we always answer that. We always answer the distance between the high voltage wiring and low voltage wiring. But for doing that, it means that we spend a lot of material, because at that time perimeter of cycle of this wiring is bigger than before. So why that? It's bigger than before. Why that? Because, and for that you can see the perimeter of the cycle of this wiring, because at that time we have to move outside this one. And also the dimensions, the total dimension of magnetic circuit of including the wirings are very big, and also the cover of the transformer are very big also. Because the cover, like the tank of the transformer, are very big. And for that we spend much money on this solution. And otherwise, and the total loss of this one is very high also. And for that, in practice, they take advantage of the space between the high voltage wiring and the iron core. Okay, they have to put the low voltage wiring in the middle. Okay, in the same way for phase B and phase C. Okay, and this one is very, very important. It's very, very important for the engineers, for the engineer, and for the factory also. Okay, factory. Yeah, for the factory. And of course, it's more important than is more important that it's more important when we are talking about the very high voltage, such as 110 kilovolt or 220 kilovolts, or even 500 kilovolt also. Okay, and also in this slide, you can see I present. Okay, I present the thickness of the lamination. It's normally from the 0.27 to 0.35 millimeter. Okay, and it's covered by an electric varnish, because as I said before, for each lamination is covered by an electric varnish to reduce hysteresis losses. Okay, hysteresis losses and the eddy current losses. Okay, keeping in mind this idea. Keeping in mind this idea is very important also. Okay, it's very important also. Yes, and for next slide, I would like to maybe I might zoom smaller. Yes, is this okay? So are you seeing something on the slide? Yes?
Yes.
Okay, I keep like this, it's better for you. You can see here, okay? And for this slide show you, and you can see show you the arrangement of magnetic circuit and also the wiring. You can see here. For example, you can see and the shape of iron core here. You can see here, and for each phase, for example, and phase A and phase B and phase C here. For each phase, we get two different wirings. Okay, have a look at this one. For example, here you can see if we are talking about the step down transformer, it means that the low voltage wiring must be located close to the core, and the outside is for the high voltage wiring. Okay, so why do you have to do like this? Because in order to answer electrical installation between the high voltage wiring and the iron core. Okay, keep in mind that idea. Okay, and of course you can see here each lamination here. Okay, each lamination, and sometimes you can see, and the shape one is not rectangular. Okay, it's a cycle. Okay, it's cycle rectangular like this one. Okay, and what is the difference with this one and that one? Okay, depending on the technology and also depending on the capacity of the transformer. Because you can see if we use the iron core cyclically, it means that the length of the wiring is shorter than we use the core like rectangular here. Okay, and of course if you look at on the right hand side, you can see the engineer are matching. Okay, engineer are matching each thin lamination. Of course in practice and practice. Okay, if you want to get each lamination like this, okay, they have to use a CNC machine to cut directly. But if you want to match for each lamination together in order to get a magnetic circuit, of course we have to do by the hand, without using CNC machine. Okay, the CNC machine is only to cut. Okay, it's only to cut each lamination. Okay, each lamination. Okay, of course here you can see even in the factory of Euro country. Okay, they are matching. Okay, yeah, matching this one. Okay, and of course in Vietnam also you can see. Okay, and in Europe country you can see everything is very professional, but in Vietnam so things because of the poor technology, and also you can see and the workers. Okay, and the worker they were matching the small small transformer. And here, if you look at quickly, even if you look at quickly, you can see, and for this magnetic circuit is bigger than this one, and for that, and capacity of this transformer is bigger than this one. Of course, depending on the side, For example, for the building and for engineers, they have to compute the load, the total load of the building, and from that they will decide to select the capacity of the transformer, and also for the generator also. Okay, generator, and from that they will select one transformer, one or two or three transformer, and then they allow all of them to work in parallel or to work independently. Okay, independently. Okay. Yes, and for this, I just show you quickly about arrangement of magnetic circuit of the transformer. And for that, you can imagine, you can visualize quickly about that. Okay, about that. Yes, and of course, after completing, for example, after completing arrangement of the magnetic circuit, okay, and how to see, they have to fix by using some, okay, you can see here, by using some belt, okay, by using some belt to wrap around of each core of the transformer like this. Okay, they have to use some bar to fix, okay, of this one. Yes, this one. Yes. Okay, we have just completing. We have just talking, completing about the magnetic circuit of the transformer. Okay, and now we continue to talk about the windings of the transformer. Okay, if you remember again, I already talked about the location of primary winding and the second winding, or we can say I have just talked about the location of low voltage winding and high voltage winding. Okay, if you know exactly the concept of primary and the secondary winding, okay, you can read the textbook, the electrical machine 1, electrical machine 2 in the laboratory. Okay, in the library, or in the bookstore, you can go to the bookstore to buy it. You can go to internet, okay, internet to download. To download is very easy. Okay, if some student learn well English, okay, you can, because for the textbook in English we get a lot. Okay, we get a lot. And of course, for the winding, and now let's say again the picture. Let's say again the picture here, you can see. Okay, let's say again picture, you can see. Of course, again the blue color and the red color here. Blue color and red color here, you can see, you can see the different winding between primary winding and secondary winding. Okay, and of course, before talking that, okay, you can see the windings. The winding are also playing an important role for any electrical machine, not only for the transformer. Okay, and of course, in the transformer, in the limitation of the transformer, we see the windings are electrical parts of the transformer, and they used to attract energy, to transmit energy. So why is that? Because you can see, and in the transformer we have two different windings. For example, if you are considering the single phase transformer, you can see we have two different windings. Okay, the first winding connected to the source. Okay, for example, for beginning winding is connected directly to the electrical system. Okay, and for another winding, okay, is connected to the load. Okay, if you look at this one, you can see two windings are not connected together. But if you apply energy in this winding and in another winding, we get energy. Okay, we get energy. So that's why you can see, and the functions of winding are used to attract or to transfer energy from this side to another side through the magnetic circuit. Okay, and the question is asked, so why do we put the energy in the beginning winding, but in another winding we get energy? Okay, based on the induction, based on the phenomena of magnetic induction, phenomena of magnetic induction. Okay, of course, about the principle of the transformer we discuss later. Okay, and also the second idea of the winding is that the windings are required to induce an electromagnetic force given in advance, and they allow the red current to go through the overheat. It means that the winding must stand. So when the winding carrying the electric current flow in it, okay, of course they have to stand. They have to stand for that. Okay, without overheat. Okay, without overheat, it's very, very important. Okay, it's very, very important. That is the function of the winding. Okay, and for the windings we get several kinds of winding. Okay, the first one is the concentric winding. Okay, it's concentric winding. You can see the picture on the right hand side of this slide. You can see a concentric winding contain many layers. Using for the high voltage winding of 35 kilovolts. If you look at here, you can see the first picture here is a concentric winding. There are a lot of layers wrapping around the core. Okay, for inside layer and for the first layer close to the core, and the second layer and the third layer. Okay, and of course you know for the high voltage it means that the current is very low, so that's why they can use the shape of the winding like this. And for example, if the capacity of the transformer is higher, it means that the current, or if the voltage level of the winding is lower, it means that the current is higher. And when the current is higher, we have to use the shape of winding like this. So we have to divide two different layers, and the rectangular. You can see the rectangular shape here. Okay, and of course, for this one is concentric winding. This one is concentric winding, and the second thing we are talking about the helical winding. Okay, helical windings. This winding is used for the low voltage winding. So why that? Because when low voltage winding, as I said a few seconds ago, and the current value is very low. In order to bring current for the low voltage winding, the current value is very high. It's not very low. It's very high, and for that, in order to bring the very high current, we have to use the cross section of the winding is very big also, and for that we cannot produce the shape of the winding like this. Okay, instead of using like this, we have to use the shape of winding like this. And the shape like this, is called helical winding. Helical winding used for the low voltage winding. Okay, and of course for this kind of winding, in each winding we get some slot in turn to turn here. So why that? Because for our winding, the embedded in the oil, because all the windings, even for the magnetic circuit of the transformer, put it in the tank of the transformer, and for that the oil go through everywhere of the winding. Okay, in order to make cooler, cooling, the cooling of that for each widening each, okay, each turn, or otherwise you can say from turn to turn we get gap, or we get a slot. You can see the slot between turn to turn here, and for that the R is very easy to go everywhere of the widening, and for that it will the temperature in the widening is reduced also, okay. And keeping in mind, and this kind of widening is called helical widening. So why is that? Because when you do the middle exam or the final exam, okay, they will show you the picture like this, and then they will ask you, for example, the finger A, finger B, finger C, and finger D, for example, and they will ask you what is the finger B, for example, okay, and then they will give you some answer, okay, and the responsibility to select the best answer, okay. And sometimes if you read some textbook, okay, they will show you, about the theory in detail, like what I'm saying, okay. And for that I would like to emphasize. I want to emphasize theory, and also I would like all of you to remember, to keep in mind, okay. And also here you can see, and of course for the continuous helical widening, where is this? And here you can see here, and this one is very important. It's very important also. And normally is for the transformer. They went for engineer, for example, engineer, even for factories, they when they design or produce a transformer, they usually use the helical windings, and that is okay. And this type of winding is used for the high voltage winding, and use rectangular wire to wood, okay, to wood into glass arranged side by side. It means that you can see instead of whopping from beginning to the end. For example, if we get 100 turns, okay, 100 turns, we can use, okay, normally if you wide from 1 turn to 100 turn, okay, it's the same, okay, it's the same, okay, it's the same thing. But here, okay, instead of whopping from 1 turn to 100, okay, we can divide 100 turns into 10 discs, or into 10 galleys. For each galleys, we get 10 turns. For each disc, okay, we get the 10 turns. Okay, and for that, it means that you can see, for example, if we get a voltage level of 22 kilovolt, if we use one winding with 1 gallet containing 100 turns, okay, and for that we have to use electrical insulation for 22 kilovolt, okay. And now if we divide 100 turns into 10 gallets, where each gallet we get 10 turns. It means that 22 kilovolt is already divide for each gallet. For example, for each gallet we have to use electrical system with 2 kilovolt only, okay, with 2 kilovolt only, without 22 kilovolt, okay. And for that, it's very easy for us to use electrical insulation. Of course, when you look at the transformer, for example, 110 kilovolt. Of course, outside of transformer is 110 kilovolt, but inside of transformer they already break 110 kilovolt into smaller voltage level. So why is that? So they have to do that in order to in order to design, in order to design easier, because for the very high voltage, it's not so easy for us to use electrical installation. Okay, in order to make it easier. Okay, of course we have to break or to break from very high voltage to low voltage, very high voltage to low voltage. For doing that, we have to use the continuous helical windings. Okay, continuous windings by wooding into glass arranged side by side like this. And of course, for this one, you can see 1, 2, 3, 4, 5, 6 glass, for example, 6 glass. In order to work from beginning to the end. Okay, of course, in one galette. Okay, they have to in one galette with very big one. Of course, we have to divide from the big galette into some small galette. For each galette, you can see the slot between the two galette together. Okay, between two galette together, and in the same way, previous way of the helical winding here. Of course, for each galette we get a slot here, and for that the oils. Okay, for that the oil of the transformer is very easy, go through everywhere of the wiring, and for that when the transformer is working with the load, and the temperature in the wiring is reduced also. Okay, so and the other idea is that, and for that one, it's very easy to use electrical installation for the wiring. Okay, and of course you can see for the low voltage, it's very easy to use electrical, and of course electrical installation. Of course, with very high voltage. Okay, high voltage is very difficult. It's very difficult, especially for the 110 kilovolt or 220 kilovolt, even for the 500 kilovolt. And of course, you can see in Vietnam, if you, I'm not sure that all of you know the Đông Anh company. Đông Anh company is always produce from the distribution transformer to the transmission transformer or transmit transformer also. And of course for the transformer of 500 kilovolt. Okay, and of course the Đông Anh company, they already produce, but what is the difficulties for designing the high voltage transformer, that is you can see that is the electrical installation for the wiring, because and even we produce a high voltage transformer of 500 kilovolt, but the idea that how to check, okay, how to test. If you want to test this one, because you can imagine that last week I was talking about the test of the transformer. Okay, the test of transformer in order to know exactly the capacity of electrical installation, using in the transformer. Okay, but in Vietnam, and also we have to test the partial discharge in the oil of the transformer. Okay, of course, for doing that, you have to get the device. to test. But in Vietnam, we don't get a lot of device to test. And for that, a few years ago, when the company when the Đông Anh transformer and Đông Anh company, they produce the high voltage transformer of 500 kilovolt. Okay, they have to send that transformer to Ukraine to test. Because in Vietnam we cannot, we don't have enough equipment to test. And for that we complete production of the transformer, but we have to send it to Ukraine country to test. And it's taken around 6 months. Okay, for moving, for testing, and for coming back to Vietnam also. And it means that you can see it takes a lot of time for that. Okay, and also because before that, before producing the high voltage transformer of 500 kilovolt, okay, we have to import from the other country. Okay, for each time, for each time we have to wait for few years, for one years, even for 2 years also. And for that we always depend on other country. Okay, and of course nowadays we have designed the high voltage transformer, but for equipment to test of this one, we don't have enough. Okay, and sometimes we have to, and also if we want to test in Vietnam, we have to invite send an expert, foreign expert from other country, and go to Vietnam to test, to supervise and or to monitor how to test, to guide us how to test also. To guide us how to test. Oh, sorry to interrupt. Okay, let's continue. Yes, and that is the difference. Okay, that is the difference of wiring of the transformer. Okay, you need to distinguish for each one. For example, for when we are talking about the concentric wiring, okay, you know, and the shape of this one from the on the top right, okay, and on the bottom right, you can see the helical windings and also continuous helical winding. Okay, for this one. Okay, yes, and for another solution, we get interleaf winding. Interleaf winding. Have a look at the picture on the top right. You can see interleaf winding. This is a type of winding which high voltage and low voltage windings are alternative wood, and this winding is wood integrated and used for the high voltage winding. In order to answer isolated distance between the high voltage winding and the magnetic circuit, as I said before, and of course, and for the low voltage winding located next to the iron core, and then we get high voltage winding. Okay, in order to answer the distance between the high voltage winding and the magnetic circuit. Okay, I already explained to all of you about that. Okay, have a look at here, you can see. And of course, for the low voltage winding is located close to the iron core, and then high voltage winding, low voltage winding, high voltage winding, low voltage winding. Okay, and high voltage is abbreviation for the HA. Okay, and CA, because here in the it's written in Vietnamese. Okay, but I have just explained to all of you. And for other things, I think is very important. It's very important for the transformer also. That is the syrup transformer. The syrup transformer lies a tank of the transformer. That one is a syrup transformer. Okay, and some textbook, syrup or cell, is designed to contain the oil, and to cool and protect the oil, and protect the oil of the transformer. And of course, on the top of the syrup transformer has input postulants. Okay, has input postulants, and of the high voltage winding and output postulate of the low voltage winding also. If you come back to previous slide, you can see postulate and high voltage postulate and low voltage postulate of the transformer located in the cover of the transformer. Okay, it's the cover plate of the transformer also. Okay, and of course you can see the conservator oil. A conservator oil is mounted on the cover on the top of the tank of the transformer also. Okay, of the tank of the transformer also. And of course, this one is just to introduce all of you to remember again. Okay, remember again. And now for next picture, I would like to show you something inside the transformer. If you make a cut, okay, if you make a cut, you can see here. So something inside the transformer. Okay, make a cross section of transformer here. You can see something like the windings and the iron core of the transformer. Of course, here you can see here the postulate, high voltage postulate of the transformer here. You can see it mounted directly on the cover plate of the transformer here, and also you can see and conservator oils, okay, mounted directly on the cover tank of the transformer. And here you can see the radiator of the transformer, and this one. And of course, there's some wing. Okay, some wing is because when you put the transformer in the basement of the buildings of the building, of course, in order to move easier, okay, you have to use some wing like this. Okay, nothing special for this one. And of course, if you look at the picture on the right hand side, you can see something in detail of the transformer here. Okay, something in detail of the transformer here. Okay, it's very, it's very, very important. Yes. And here, okay, I'm going to tell you about this slide. This slide you can see and location of the windings around iron core of the winding. Okay, and of course this one. And this one, okay, I'm going to ask you about this notation, okay, and it doesn't it's 1 or 2 minutes later. And here's a high voltage winding. You can see high voltage winding. If you look at the winding, if you see the cross section of the winding, is very low. It means that the voltage is very high. It's very, very high. Okay, of course you can get that is the high voltage winding. And of course, look at on the right hand side here, you can see, and the windings the winding is designed into some gallet. For example, here 1, 2, 3, 4 gallets. For each gallet occupied, for each gallet is corresponding to, for example, if the voltage level of each winding is 22 kilovolt. 22 kilovolt. And now if we divide the big winding into 4 gallets like this, it means that for each winding is corresponding to each gallet is corresponding to the 5.5 kilovolt. 5.5 kilovolt. Yes, 5.5 kilovolt. And for that, it's easier for us to use electrical insulation. Okay, instead of using electrical insulation for the voltage level of 22 kilovolt. 22 kilovolt is very, very expensive. Okay, if you consider for higher voltage level like 110 or 220 kilovolt, or even for 500 kilovolt, it's very, very difficult for us to use. Okay, and even you can see the high voltage transformer of 500 kilovolt, but inside of the transformer, and from the postulate high voltage, of course, is 500 kilovolt, but inside the transformer, the high voltage transformer is already break into lower voltage by using continuous helical windings. And I said a few minutes ago, even now, okay, okay. The question is, and now when we come back to this picture, I would like to ask you, okay, and the notation like this. Let me write. Okay, let me write again 150. Of course, here 20. Up here 10, for example, up here 0.4 kilovolt. Okay, according to you, can you please explain? Can you please explain to me and what is the meaning of this load of this notation of this notation? Can you please explain? Okay, I would like, maybe I think I would like to give you 10 minutes, and I would like to give you 10 minutes, okay, for a time break, okay, and for time break, and in parallel you can think about my questions. Okay, I will come back to our lecture in 10 minutes. Is this okay?
Yes.
Yes, okay. Okay, I will come back to you. I will come back to you in 10 minutes. Maybe I think around the 12 minutes. Yes. Okay, let's come back to our lecture. Yes, who can answer my questions? Okay. Are you hearing something from me or not?
Yes.
Yes, okay. Yes, so as I said before, if we have, okay, the notation like this, you can have a look at this one. You can see the notation 150, 20, and 10, and 0.4 kilovolt here, okay? And I would like to ask you, what is the meaning of 150 here? Okay, can you explain to me? Who can answer my questions? Who can answer my questions? Who can answer my questions? Okay, please raise your hand if you know.
I think it is step down transformer from 150 kilovolt to 22 and 10 and 0.4 kilovolt.
Okay, about yes, the first answer is that step down transformer is correct, exactly. Okay, so when you are talking about the voltage level like 100, okay, from the 200 and 22 kilovolt is okay, right? 10 kilovolt is okay, right? 0.4 kilovolt, right? But the number of 150. You were talking, okay, you were talking this, you are talking about the high voltage level is not correct, okay, because the 150 is not a high, it's not a voltage level, okay, it's not voltage level. Of course, I would like to explain a little bit to you. Okay, and this one is step down voltage, but we have two different input voltage level. 22 kilovolt, 10 kilovolt, but for the output voltage level is only one. It's only one level. That is 0.4 kilovolt. 0.4 kilovolt. And so why do you have to use two different input voltage level for transformer? Normally, if you go to the station, for example, if you go to the transformer station, for example, go to the high buildings, hospital, for example, airport or commercial center. Okay, you can see the transformer of 22 kilovolt and 0.4 kilovolt without the voltage level of 10 kilovolt. But for this case, we have two different input voltage level. So why do you have to use like this? Okay, because you can see, for example, and now you know the bank group, and now the bank group they invest a lot of and they build a lot of house building and also commercial center. Okay, they have to use because, and of course we have to use the transformer for the highest buildings for commercial center. For example, in countryside, not in Hanoi, countryside, you can see in countryside normally for the countryside they still use two different two different voltage level or otherwise. Now it's current using for example the 10 kilovolt, but in the near future for EVN company they don't allow use 10 kilovolt anymore. Okay, instead of using 10 kilovolt they have to replace all the 10 kilovolt, all the voltage level of 10 kilovolt everywhere by using 22 kilovolt. Okay, for example, in the near future. But now they're still using this. They are still using the voltage level of 10 kilovolt, and for that we have to use corresponding transformer for this voltage level by using 10 kilovolt. For example, 2 years later, okay, 2 years later, or next 2 years, okay, and the voltage level of 10 kilovolt don't use anymore, okay, 10 kilovolt, the voltage level doesn't use anymore, okay, we have to replace by from 10 kilovolt by 22 kilovolt, okay, and for that we cannot replace transformer, spend much money on that, okay, and from now, okay, in order to use the voltage level of 22 kilovolt, from now we have to use the 2 different input voltage level for transformer, which is 22 kilovolt and 10 kilovolt, and of course output voltage is the same, okay, the same 0.4 kilovolt, okay, and now we can use the 10 kilovolt, and then in the future, we don't use 10 kilovolt anymore, okay, we can use 22 kilovolt for the transformer, and for that we don't have to replace the transformer, we have to replace by another one, okay, we don't spend much money on that, okay, and that's why, and for this transformer we have to use 2 different input voltage transformer, okay, and the idea is that, and how about the 150 here, what is the value of this one, and this one is you can see is the power of the transformer, it's the power of transformer, okay, it's not the voltage of transformer, it's power of transformer, it's the capacity of power of transformer, okay, you understand what I'm saying, it's power, okay, and power of transformer, okay, and normally because in Hanoi, okay, in Hanoi, so we get only one voltage level, that is the 22 kilovolt, okay, for example, we let me write, for example, the 1,000, okay, kVA, you can see 22, okay, 0.4 kilovolt, okay, something like this, and of course here we can write like this, 150 kVA, okay, and here you can see 0.4 kilovolt, like this one, okay, and of course this is power, apparent power, okay, apparent power, okay, because in transformer we have to some kind of power, apparent power, you know, and the unit of apparent power, that is the kVA, okay, or VA, depending on the capacity, okay, and also we get active power, the P, okay, because here you can see normally we get S, okay, is equal to square S, okay, maybe I think I would like to use like this, I think it's better for here you can understand. I don't. And here, okay, for example, you can see, and let me check with this one, okay, it's just P square of root like this, okay, plus Q here, and okay, and where P is the active power, and let me turn off, yeah, power, and Q is the reactive power, yes, and of course this one's the unique curve, okay, this one, okay, and here you can see the unit sometimes kilowatt, okay, is this one, yes, this you can see, and of course this one, okay, and 150 kVA, where we get P, we get how many percentage of reactive power and how many percentage of reactive power, depending on the power factor of the transformer. Okay, depending on the power factor of transformer, because you know exactly. For example, if they give you the capacity of the transformer 150 kVA, okay, and for this one can supply for how many active powers for the building, for example, for the building, okay, in order to, and also how many reactive powers for the building, okay. So of course you have, if you want to compute, reactive power, of course you have to know exactly the values of the power factor of the transformer, normally for the transformer, and also power factor of the transformer and the power factor of the load. Okay, and normally, so for the transformer, in order to increase the power factor of the transformer, they have to use some capacitor to increase the power factor of the transformer. Okay, yes, for that why. And now you know well about this notation. Okay, this notation here. Yes, this one. Yes, because if you don't understand, please ask me right away. Okay, I would like to re-explain to you. Okay, to re-explain to you. Yes, and of course this picture also show you about the total. Okay, about the total space of factory. You can see everything is very clean. It's very clean. Okay, the nose. Yes, no hermit and no something you can see here, even for the background, and also some electrical machine here for the engineer. They are working on the machine, okay, and then even for some packet like this. Yes, and of course, and here picture is nearer for you to visualize. And of course, and here there are two engineers are working for the ABB company. So you know the ABB company produces a lot of transformers, even for the step-down transformer and step-up transformers and other equipment also. And every year there are many engineers graduated from the School of Electrical Engineering, working for this company. And of course, I don't know exactly, depending on the position, and the salary is very high also. It's very high also. Okay, when you are still student for the 4 years or 3 years student. Okay, you can do internship for this company. You can do internship for this company also, and of course you can get I don't know exactly, but you can get a small amount scholarship for the internship, because every years, okay, this company always send a letter, the invitation letter to the dean of school of dean of School of Electrical Engineering, and also send all the students to see. If you go to the website of our factory, our school, okay, you can see, and there are a lot of recruitment for internship and also for the engineers, and for that you can apply for the position when you graduated from the Hà Nội University of Technology. Okay, and this one you can see, and the people and the engineer, they are completing the wiring of the transformer, okay, by using some special equipment, okay, to make the surface of the wiring better, okay, better. That is one. Okay, and now it's time for us to talk about the transformer principle of the transformer. Okay, and up to now, let's say again, you understand very well about the concept of transformer and also the application of transformer and something in details outside and inside, and also the magnetic circuit, magnetic iron course of windings, how many types of winding are used in transformer. Okay, concentric winding, for example, and helical winding and continuous helical winding and something else. Okay, and of course we also talk about the notation of transformer. When you read some textbook, if you get some trouble, okay, you can come back to our lecture. You can get some idea to explain. Okay, and of course I also show you some general picture of the factory and of course you are familiar with the transformer already. And now, and this part, I am talking about the principle of the transformer. Okay, in order to answer these questions, okay, have a look at the picture on this slide. On this slide, you can see, in order to be simple, okay, I would like to show you a single phase transformer, because for the three-phase transformer is the same in the similar way of talking about that. And here, in order to be simple, I would like to talk about the single phase transformer like this. And here you can see, and now, and you can guess right away, this is the magnetic circuit. This is magnetic circuit or iron core, including two different winding. The first winding, if you look at on the left-hand side with the red color, okay, and also the second winding is the green color, okay. And for example, here, if we are considering this transformer, this single phase transformer as a step down transformer. It means that, and for the first winding, we can call the primary winding. Okay, primary winding is connected to the high voltage, and for example, the electrical system of 22 kilovolt. It means that the primary winding with the red color is connected to the voltage level of 22 kilovolt. Okay, and of course, and for the second winding is a secondary winding. So a secondary winding is connected to the load here. Of course, we don't know exactly the value of the load in advance. Okay, and have a look at this finger carefully. You can see two different are not connected together. Okay, you can see, and this winding is winding around the core of the transformer, and here also. Okay, you can see here separately, and the two winding are separately. Okay, without connecting together, and of course here you can see, and the iron core. Okay, iron core. Okay, and the question is that, as I said before, when we apply the high voltage of 22 kilovolt here of electrical system into primary winding, okay, even two winding are separate, okay, are separated together, but in the secondary winding, okay, still getting the electrical current flowing in the load. Okay, of course, if the load is connected directly to the primary winding here. Okay, so why that? Of course, as I said before, based on the electromagnetic induction. Okay, even two winding are separated. Okay, but when we apply the voltage in the primary winding, in the output voltage still gets electrical current flowing in the load. Okay, in the load. Okay, now let me explain to all of you about that. And once you understand very well about the principle of the transformer, okay, so when we go to the next part, okay, and you can understand easier. Okay, have a look at this picture. You can see is when we apply the voltage apply the high voltage level of 22 kilovolt with E1. Okay, you can see, and the one primary winding with the number turned W1. Okay, when we apply the voltage in the primary windings, okay, we get a current flowing in the winding. Okay, as we said before, and when we get the current flowing in the winding, it means that we get a magnetic field, or otherwise we can say in advance we get a magnetomotive force F. F is equal to current. Okay, current flowing in the windings. For example, here current one, and right like this, multiplied by W1. Okay, and the unit ampere turn. Okay, the unit ampere turn here. Okay, ampere turn, the unit ampere turn. This, okay, and this one you can, when we get the current flowing in the primary winding, it means that we get a magnetomotive force. Okay, magnetic force due to the current in this. Okay, and thanks to the magnetomotive force F, okay, we can get the magnetic field, magnetic flux, okay, flowing around the magnetic circuit here. Okay, we get, okay, and phi here, so maybe I write phi here instead of using the mathematical tool. Okay, is equal to F divided by RG. Okay, RG. Okay, so where F, okay, where F is the, you can see, okay, let me, is the magnetomotive force, and it's the reductance of reaction of the magnetic circuit. Yes, the magnetic circuit. You can see reaction of magnetic circuit. It means that you can see, for example, if we don't get magnetic circuit, we put two winding next together. Even we put close together without touching. Okay, of course. When we, of course, you can see at that time, and RG is not RG. It's also reductance. It's also reductance of the air. But because the winding would around the iron core of magnetic circuit here, and the cone RG is the reductance of magnetic circuit. Because of that, you can see normally the reductance of magnetic circuit is very, very small in comparison with the one of the air. It's the one of the air. Or we can say the reductance of magnetic circuit is very small in comparison with the reductance of the air. Okay, and for that you can see in the electrical diagram. If the resistance is very low, it means that the current will flow in that space. Okay, and at anywhere getting the low resistance, we get current flowing in it. Of course, in magnetic circuit, so when the reductance is very, very small, it means that the magnetic flux phi here is very high also, because the phi here is the same, because here, so we cannot, or we can use the math symbol, here. Okay, let me check the math symbol here. I think we can, yes, here math, even here we can use math symbol like this. Okay, no problem. I would like to use the math symbol phi. You can understand better. Here, yes, right. You can see here, yes, magnetic flux flowing around the magnetic circuit here. Okay, we get phi equal here. So thanks to the based on or thanks due to the magnetic circuit, and the reluctance is very small, and for that the magnetic flux is very high. Okay, and of course, and now let's say again, when we apply the voltage into to the primary windings, of course we get a current flowing in the winding, and we induce a magnetic circuit. Okay, a magnetic field flowing in the magnetic circuit, which can be defined by F. Okay, by F divided by Rg, where F is the magnetomotive force, and Rg is the reluctance of magnetic circuit. Okay, and you can see the magnetic field. Okay, distribute continuous around the magnetic circuit here. Okay, if you combine to the Faraday law, okay, Faraday law, you can see when we get the magnetic flux, okay, going up and going down according to the time, it means that we get induced voltage or electromagnetic force E1, okay, appearing in the winding W1, and of course in the W2, you can see in W2 in the secondary winding we can get also the diffusion of magnetic flux to the window of this one, alternatively, okay, of this one, and of course, and when induce the electromagnetic force in W2, E2 here, of course. And for beginning, if we don't connect, okay, if this doesn't connect to the load, it means that here we get electromagnetic force E2 here is equal to U2 without connecting. Of course, the unit of electromagnetic force, as I said before, also is also the volt. And last time I asked you to answer me questions, and when we call electromagnetic force and when we call the voltage, okay, and now let's say again, so when the load, with the low load, it means that we get electromagnetic force E2, okay, and if the wiring is connected to the load, it means that we have the voltage, also, okay. And of course, if the wiring is not connected to the load, and it means that the output of the secondary wiring is open. According to you, there will be an electrical current flowing in the wiring or not. If the secondary wiring is opened, according to you, there will be an electrical current flowing in the load or not, or in the wiring. And the wiring is better for you to answer these questions. Please answer me questions. No? So you think, so you can see when the secondary wiring is not connected to the load, it means that the wiring is open. So when the wiring is open, there are no an electrical current flowing in the load. It means that the current value is equal to 0. It means that we get the E2 is equal to U2. Okay, and now if we connect the wiring to the load, it means that you can see here is we can get the electrical current flowing is a load. Okay, and if you come back to the beginning, you can see when we apply the voltage you want, okay, in the primary wiring, okay, in the secondary wiring we get the voltage here. If the waveform is a waveform of the primary voltage is the sinusoidal. Okay, it's sinusoidal. It means that the magnetic field due to the current flowing in the winding is also sinusoidal. It's also the sinusoidal and has the expression like this. Expression like this. And phi is equal to phi max sin over sine over 10. Okay, where omega is equal to 2 pi multiply the frequency here. Okay, and of course, as I said before, so when we get distribution of electromagnetic flux, okay, flux will induce the electromagnetic force E1 in W1 and E2 in W2. And if the W2 is connected to the load, it means that we get the current flowing in the load. And of course, we get applied voltage on the load also. Okay, on the load also. And of course, have a look at this figure. You can see even two winding and are separated together, but when we apply the voltage in the beginning winding, of course, in the second winding we get the voltage. And for that, you can see the function of the winding is to attract the input energy and also to transfer from the input energy to the another winding. And of course, what is the function? And the function in order to take the magnetic field from the primary windings to the secondary winding fastly. So fastly, okay, fastly. It means that you can see, you can imagine that. And so why does the energy transfer from the primary winding to the secondary winding based on the magnetic field? Based on the magnetic field. Okay, and of course, the magnetic field is very, very important. Okay, in order to produce a transformer and also in order to produce the induction motor and generator. It means that we can convert from the mechanical energy to electrical energy, and inversely from the electrical energy to mechanical energy. Okay, and from the mechanical energy to electrical energy, it means that we are talking for the generator. Okay, and from the electrical energy to mechanical energy is for the motor, and like for the ceiling fan and the table fan and other things that you see in practice. Okay, that you see in practice. Okay, and of course for the waveform of applied voltage is sinusoidal, and also the waveform of magnetic field is sinusoidal, and for that we get it like expression. Okay, and once we get magnetic field flowing in the iron core of the transformer, and now how to define the electromagnetic force appearing induced in the primary winding, and also electromagnetic force induced in the secondary winding. Okay, and for next slide I would like to show you and the way of defining the values of effective electromagnetic force of primary winding and secondary winding. Okay, and here because of the waveform of magnetic field, okay, following to the time, and for that we get E1. Okay, and for this expression, you know, from the based on the Faraday law, we get E1 is equal to minus W1 multiplied by derivative of phi. Okay, here phi here, and as I said a few seconds ago, you can see the waveform of phi is a sinusoidal, and for that, when we take the derivative of phi, it means that we get the derivative of sinusoidal is equal to cosine, and for that one we get this one, and of course it's mathematically, okay, nothing special on that. Okay, and from this we can transform from this to this also. Okay, if you good at math, okay, it's very easy for you to transform or to deduce from this impression to that impression. Okay, in the same way we can get a transformation of electromagnetic force in the secondary windings divided by this one. Okay, Okay, and of course, have a look at this expression and that expression. You can see E1 and E2, and I said a few seconds ago, are effective values of electromagnetic force of the primary and the secondary winding as well. Okay, as well. And of course, you can see, and of course, and here you can see E1 is normal. E1 is normal, normal writing, normal, and in capital writing here you can see is easy, and it's the and their effective value. Of course, and how to define this effective values. Okay, you can see instead of writing like this, we get so E1. Okay, you can see here E1 is equal to W1. Okay, E1 equal to W1 multiplied by omega multiplied by 5 max here. Okay, we get this one. Yeah, divided by square of root 2 is this one. And you can see W1 is the number term as primary winding. W2 is number term as secondary winding. And omega, how to define omega? Omega is equal to 2 pi multiplied by frequency. Okay, frequency. The pi is a constant frequency. Okay, here W1 5 max. Okay, and of course here is constant also. Okay, in order to write shortly, we can replace by this one. Replace this one by that one. We can get E1 is equal to 4.44 multiplied by frequency W1 5 max. Okay, in the same way, in the similar way, we get E2 also. And of course, you can see, have a look at this one. You can see, and E1 and E2 are the same frequency, because you can see frequency is the same, and the same magnetic field also. And the only difference is that the number turn of the primary winding and the number turn of the secondary winding, only. Okay, yes. And for that, you can see if you take the ratio of primary induced voltage or the ratio of the electromagnetic force of primary winding to the secondary winding. Okay, we can get like this. Okay, you can get like this because of the same frequency, the same electromagnetic field, and for that we get E1 divided by E2 is equal to W1 W2. And instead of writing like this, we can denote W1 divided by W2 is equal to K. K is the ratio of the transformer. The ratio of the transformer or some textbook written transformer ratio. Keeping in mind this one. Okay, this one. Okay, and from that, so for example, if the voltage drop, if the windings are neglected, it means that we get W1 divided by W2 is appropriately equal to is the appropriately U1 divided by U2 here, and from that we can deduce this expression. Okay, keeping in mind, maybe I think it's high time for us to wrap here, because you have to have a lunch. Okay, you have to have lunch, and for preparing something in the afternoon. Okay, and for that I stop talking our lecture here, and next week we will continue to explain something in detail of this expression. It's very, very interesting. Okay, we stop talking here. Okay. Hello. Okay. So I think when I'm asking you, I think the monitor should answer me right away. Okay. I think it's better for me because for that I don't have to repeat. I have to repeat asking you. Okay. Okay. Stop talking here. See you next week. It's okay if you don't understand our lecture. Okay, my lecture. Okay, please don't hesitate. Email to me. Okay, I would like to explain again. In Vietnamese. Okay. Okay. Thank you very much for your attention. Okay, let me turn off my computer. I have to prepare my lunch. Okay.